Well, good evening and welcome to Space Oddities. Thank you for joining us on this Tuesday evening. We are the usual rabble this evening. I've got Roger, Michael and Daz joining me this evening. How are you guys?
Fine, thank you.
Good.
All well here.
Oh,
Good.
lovely. Oh, lovely.
So, on tonight's show, we are going to take a look at the first decade of the new science of gravitational wave astronomy, which is a brand new science. And the actual first discovery happened in 2015. It was actually in September, but I was so excited about it. I thought I would do a summary now of where gravitational wave astronomy is, what it's discovered and what the future holds. So we got that coming up a bit later. And also this evening, Daz is going to be telling us a little about something that was in the news over Christmas and continues to be in the news, namely the Parker Solar Probe. So we've got an interesting look at that and a few other odds and ends. So we hope you're all well. Thank you for joining us. Let's have a look in the chat. Let's see which reprobates we have in this evening. Jerry's here. Hello, Anne. How are you? Hope you and Mick are fine. Hi, Kev. Hi, Stuart. And I think David was here earlier. Not sure if he still is. Derek's here. Hello, Derek. How are you? Good to see you all. And we've got a bit of a busy week on Space Oddities because we've got several space launches happening this week. You may be aware that we did the other morning, we did the live coverage of Blue Origin's New Glenn, the first maiden flight of New Glenn, which was aborted after we sat here for hours waiting for things to happen, and the countdown kept being put back by 20 minutes every so often. They had a problem with one of the rocket subsystems that they had to fix, so it was scrubbed for the day. Interestingly, historically, no brand new rocket has ever launched on the first attempt. It's never been done. So the odds were against Blue Origin launching on the first attempt. The launch is now rescheduled for Thursday at 6 a.m. UK time. So we will bring you live coverage of the second attempt to launch the New Glenn rocket. Tomorrow morning, very early again, we will be covering the launch of the Blue Ghost lander to the moon on the SpaceX Falcon 9 rocket. And we're looking forward to that because it's the first mission to the moon this year. It's the first time that America have landed in Mare Crisium, the Sea of Crises on the moon. If you look at the moon, it's that sort of dark splodge at the top right of the moon. And America's never landed there before. The Russians tried to land there in the 1960s, and that didn't work. That failed. So we're looking forward to the launch tomorrow. We should also mention that a Japanese rover is hitching a ride as well. So there are actually two landers heading to the moon tomorrow morning on a Falcon 9. So we'll be with you at, I think it's 5:45 UK, if I remember rightly. So if you can join us that early in the morning, if you're insomniac or you've got absolutely nothing better to do at that time in the morning, we'd love to have your company. Also, on Wednesday, tomorrow, we have in the evening at 10 o'clock UK time, the launch of SpaceX's Starship on its 7th test flight. Now, this test flight promises to be quite amazing, doing things that no test flight has done before, and always moving forward with the technology and what the Starship does. And as a part of the mission tomorrow evening, they will be trying to launch 10 Starlink satellite or simulated Starlink satellites from the Starship to prove that the payload deployment system works, and other things as well. So that's exciting. If you do want to find out what's going on at Space Oddities at any time, then you can visit our website, and you will see on the front page of the website, we've got all of our events coming up that you can have a look at, so you know what's going on with Space Oddities. Just lastly, I will mention it again. In February, we will be hosting a get-together between two astronauts from the Polaris Dawn mission, which flew in September. And at the moment, well over 200 children in 4 British schools. We're getting them together with the astronauts so the children can ask their questions. That's on February the 4th at 2 in the afternoon UK time, and we're really looking forward to that because we've been working with the Polaris project on that, and we're very excited to inspire these children to literally reach for the stars, which is what it's all about. So there we are. So that's what we've got coming up.
People are saying that on YouTube that the I don't know whether they're getting a lag or whether or not. I did notice for a while that the image was jumping. The sound was fine, but the image was jumping
Right.
back and forwards. But some people are saying that there's a lag on the sound. Can I just suggest that people, because all I did was just stop the video, come off of it, went back on again, and it's working as well as can be. If there is a lag, unfortunately, there's not a lot we can do about any lags.
Sure.
Between sound and lip sync. So
the first thing to do is to refresh your browser, which should cure it. Don't just do an F5 to refresh the browser, because that'll use your cached copy. Press Control F5 on your keyboard, which will reload it from the server, and let's see if that cures the problem. Because let me just check where I am. Give me 1 second, and I will look into this. And let's have a look here and see what's happening, just to see. What's going on here? Just bear with us 1 second. Obviously, if there's a problem, then it's a few seconds behind on my YouTube here, which is, that's normal, because it does take time for the signal to work its way through the network and end up on YouTube. Just 2 or 3 seconds behind on my YouTube. So if you're having problems in the UK, then it could be, yes, Kevin says it didn't work. Well, that is beyond our control, I'm afraid. There's nothing that we can do about that. Whether there's a slow server in the UK somewhere that's lagging, I couldn't tell you. Gerard, thank you very much.
Whether or not if the actual image is smooth, or is it actually jerky?
Yeah,
because it seems to be running smooth now. I think there's just a lag on the voice and image.
Yeah. I mean, if you can watch it, if the sound and video are synchronized, that's oh, okay. It's not okay. Just won't look at your mouse. Yeah, probably wise, Kev. Yeah, apologies for that. Got no idea what's causing that. It might be a server in the UK that's lagging behind for whatever reason, but I think it obviously depends where you are in the UK, because it's fine for DAS.
There seems to be a lag between the sound and the lip sync. That's the only thing we got at the moment. It's about a second behind.
Right. Well, viewers, if you could possibly put up with that, let's see if it corrects itself later. If you could let us know in a little while whether it's still like it, then I will take it up with our streaming provider tomorrow and give them an earful. But unfortunately, it's way beyond our control. There's nothing we can do here to affect it.
Well, it won't matter when we've got the presentations anyway. So
no, that's true. That's true.
So there we go.
Speaking of which, yeah, apologies for that, viewers, but there's nothing that we can do about it. It's way beyond us. Speaking of which, let's move on to Roger's presentation. As usual, Roger's going to tell us about the night sky, and we'll have a look at the viewers gallery for this week. So
yes, we will.
Take it away, Roger.
Okie dokie. So here we go for the upcoming week, working our way through January, and as we can see, we've just passed the wolf moon, as the North Americans like to call it, for January, and we're obviously progressing onto the waning gibbous phase now. Should you be able to have any clear skies to see any of it. But through the week at midnight on these illustrations I have here, we've still got Jupiter and Mars dominating the southern skies, with the moon gradually working its way back towards the eastern skies. And we've also got our lovely favourite constellation of Orion still in glorious situ, and Sirius in a dominant southern position. So all's well and good. But as you can see now, we're gradually working our way through to Leo and Virgo, and we know what that means, galaxy season. So as we obviously progress through the month, things do gradually change, as they do with Jupiter and Mars still being very dominant. But shortly before sunset, we do have Venus and Saturn quite close to each other. So that's quite an interesting sight to see. But unfortunately for us, as you can see near the sun, we've got comets C24G3 Atlas, which is currently at an estimated minus 3.4. But due to the fact it's so close to the sun, when where it is at the moment, where we've got a lost opportunity there. But there have been some interesting pictures through the solar probes to show how bright and close it is at the sun, near the sun at the moment. So whether we'll see.
I have seen some people been able to image it, but as you said, it's virtually blown out by the sun. But it's got quite a long tail, I must admit, from what I've seen. So if you get a chance, have a go.
Yeah, it's a shame that.
And remember, if you're anywhere near the sun, filters.
Yes, definitely. But as you can see through the week, Venus and Saturn do sort of do a bit of a close encounter, so that would be quite an interesting sight to see through the latter part of the week. So keep your eyes open for a clear sky on that. Right, okay, so here we go for this week's gallery, and we have had another interesting collection of images from our regulars. Here's our first of 3 from Graham of the moon, which he did back in October. Surely it's not been that long since you last saw it, I'm sure, Graham. But this is what he's managed to do.
Oh, that's lovely. Look.
Very nice. Lots of details there. Well done. Good old sea star.
Lovely, yeah, good old sea star.
And he's got a close-up here of Mare Imbrium, which was also done with the sea star.
Oh, that's lovely.
Very nice.
What was that? That was 4 images, was it? That you said?
No, that was a ×4 magnification.
Oh, ×4, sorry.
Yeah.
Yes.
Yeah, that's lovely. I mean, look at
all the details.
Appenine Mountains. Lovely.
Yeah, you got the valley through there and all sorts, and the Mount Pico and all the rest of it. So well done. Very good. And his last one, which was of Jupiter and the Galilean moons with his sea star.
Oh, lovely.
All nicely lined up there.
Yeah.
Well done.
That's lovely.
If we can perhaps get a multiple exposure and do a composite one where you can try and reduce the exposure, so we've got the belts on there, that would come out even more spectacular.
Yeah.
A combination with the with a corrected exposure on there. But there we go. So Jerry has managed to get the Monkey Head Nebula, but I don't think it's in Orion, is it?
It's just off Orion. It's not far.
I don't think it's not designated as being in Orion, is it?
I don't think it's in the constellation. I think it's far enough away to be out of it, but it's close. I know it's close.
Yeah. Anyway, he's got this rather spectacular image of it.
That's nice.
Wow.
That is lovely, isn't it?
Very nice.
Very nice indeed.
He's done well with that one.
There's some good definition at sort of top left there, isn't there?
Wow. Lovely.
Yeah.
Well done, Jerry.
I mean, with this orientation, you can actually sort of make out a monkey shape there, with the eyebrows and stuff over the top part.
Yeah.
So So it does, in fact, sort of justify its name from that way.
Yeah. Wow.
Anyway.
And if you look at, sorry,
Okay.
if you look towards the
Oh,
bottom
sorry.
of that one, if you look below halfway and towards the center, if you look, there's a faint, looks a lot more like a capuchin type face of a monkey at the bottom in the center, just slightly off right on the center. So
Okay.
look
yeah,
look
Oh,
below.
yeah. Yes.
Yeah.
I see. Yeah.
Yeah.
Ooh.
Oh, no one looking.
What the
They're all
mind,
looking
what the
now.
mind makes out of shapes and shadows.
Absolutely.
Was it paradilio or something they call
Yeah,
it?
Yeah.
pareidolia.
Yes.
Yeah.
Yep. That's the one. Paraphernalia.
Yeah. That looks
Okay.
like Vladimir Putin.
Right. So Ian's trying to get a better phone on this one, but I'm guessing that this image here we've got down on the bottom left here is another one with the moon and Saturn, maybe, or is it Mars this time? I'm not sure. I wasn't aware of what that one is, but there we go.
Yeah, it's one of the planets, isn't it?
Yes, I would have thought so.
I think it's Mars, isn't it, by the look of it?
So here's one of mine from the other night of just before the wolf moon appeared. So this was just the day before. So unfortunately, it was so cloudy I couldn't even get anything through the clouds last night to get a full moon. But this is close enough.
Oh, that's magnificent, isn't it? You've also got a touch of Bailey's beads around the edge.
And a few nights before that, over the 10th and the 11th, through that night, I tried to get Mars and Jupiter. And the seeing wasn't very good, so they are very blurry. But I managed to get some details because through this week, on the 16th, this Thursday, Mars is at opposition. So that's the. So it's at its biggest, although it's never going to be as good as it was about 6 years ago, unfortunately. But it's not a bad size, but you can get some details, which I sort of got. I think that's Syrtis Major just to the left of centre there.
We should point out that these are not to scale.
No.
Mars,
definitely.
Jupiter.
I mean, if Mars was that close at opposition, we'd all be getting fantastic pictures, but not to be, I'm afraid.
And we'll probably get some good tides as well.
Oh, probably.
Yes, probably.
Okay, so there we go.
Thank you very much, Roger. That's great. So keep your images coming in, viewers. If you would like to send us an image for the gallery, then please attach it to an email. Address that email to gallery@spaceoddities.space and send it to us. And not only would it appear here on our Tuesday live stream, but you will also have it in your own gallery on the Space Oddities website. So what more could you want out of life, eh? So yes, please do send it to us in an email. One image per email, please, just to make it easy for us to deal with it. So thank you very much, and please, for those of you that contribute regularly to the gallery, please do keep them coming because we love them, and I'm sure the rest of our viewers do as well. Okay, let's move on. I want to talk to you this evening about gravitational waves. Just a bit of background on this. The original gravitational waves were predicted by Einstein in the general theory of relativity. He sort of, before he even wrote the general theory of relativity, was thinking about whether gravity travels in waves. That was one of Einstein's great gifts, because Einstein was not a scientist in the sense of doing experiments type of scientist. Everything was in his head. He was a theorizer, not a practical scientist, if you like. And when he wrote the general theory of relativity, these gravitational waves sort of popped out of his equations. For more than 30 years, he actually hummed and hawed over whether they actually exist. He couldn't quite bring himself to believe they exist, but eventually he accepted that they did. But he thought that humans would never, ever have the technology to detect gravitational waves because they are so very tiny. And in the late 70s and 1980s, scientists wondered whether we might be able to develop the technology to detect them. And sure enough, eventually the LIGO detector, the laser-interferometer gravitational wave observatory, was born, and in 2015 it made the first detections. I don't want to go too much into what gravitational waves are and how they work, because we have videos on that on the Space Oddities channel. If you look in the Astronomy Basics series, you will find a video all about gravitational waves. So what I want to do today is just to talk about the first 10 years since 2015 of their observation, what we've discovered, and what the future holds. So just give me 1 second, and I will put this up on the screen for you. Okay, hope you can see that. So gravitational waves, the science of gravitational waves is a completely new science. And you know, it's not often that humans live during the time when a completely new science comes about. So we're very lucky to live in this time. And as of, well, so let me just explain the way that they do it. So we've got 4 gravitational wave observatories observing at the moment. The 2 LIGO detectors in the US, the CAGRA gravitational wave detector in Japan, and the Virgo gravitational wave detector in Europe. And they observe together simultaneously. One of the advantages of having several gravitational wave observatories is that it enables you a lot easier to triangulate on the sky exactly where the gravitational waves originated. And we've now got them observing together. And they basically do what are called observing runs, lasting about a year each. And at the end of each observing run, they put together all their data and correlate it and put it together and bring out some figures. The current observing run, which I think ends in about Easter this year, is 04, observing run 4. We haven't had the figures for that yet. So these figures are all based up to the end of 03, 2023. So these are the figures. And here's a general breakdown. Basically, around 200 gravitational wave detections have been made. About 90% of these have been from binary black hole mergers. Now, black hole mergers are a lot easier to detect than other types of events, simply because black holes have more mass and they produce stronger gravitational wave signals than other objects. So they are actually a lot easier to detect. So this may be a sort of a selection bias going on here, but nonetheless, about 90% of all the detections so far have been from binary black hole mergers. 2 or 3 of them have been from merging neutron stars. And there was a famous one, which I've talked about on this channel before, the famous GW 170817 in 2017, a humongous explosion in a galaxy called NGC 4993. And there have been 2 or 3 of those types of events detected. How do we distinguish between the different types of gravitational waves events? Well, it's simply because the gravitational wave signal looks a lot different. For example, black hole mergers, the signals tend to last for a few tenths of seconds. The first neutron star merger, the famous one in 2017, it lasted for nearly a minute. And what the scientists do, they run countless computer simulations to show what the signal would look like from this type of object with this much mass. So when they do receive an event, they can match it against the nearest simulation, so they know exactly what they're looking at. There have also been a couple of mixed mergers, that is to say, a black hole and a neutron star. These are quite rare, but just 1 or 2 have been detected. And there's also been 1 or 2 events that have been in the so-called mass gap range. This is between 2.3 and 5 solar masses. This gap is between the heaviest neutron star, the heaviest neutron star we think can exist, and the lightest black hole. So the heaviest neutron star we think can exist is around 2.3 solar masses, and the lightest black hole that we believe can exist is around 5 solar masses. And obviously there's a gap between those, which is, funnily enough, known as the mass gap. So the example here, GW 190814, 190814 being the date of the detection. This featured a 2.6 solar mass secondary component. So one of the components was a black hole, but there was something else that merged with it or collided with it. We think it was a merger, but we're not sure. This was 2.6 solar masses. So this could either be the most massive neutron star ever detected or the lightest black hole ever detected. But there have been just 1 or 2 of these mass gap events where we're not sure what the secondary component was, whether it's a heavy neutron star or a light black hole. Lots of work to do on that still, obviously. So let's go through the timeline of what happened. I won't read everything, but here are the basic bones. So the first detection was made on September the 14th, 2015. Astronomers then spent 6 months trying to prove that what they had detected was not gravitational waves and failed to do so. And it was finally announced on February the 11th, 2016. And it was a black hole merger 1.3 billion light years away. In other words, it happened 1.3 billion years ago, because gravitational wave signals do travel at the speed of light, which was another key confirmation of general relativity. They were hoping that they would get a second event detected so that they could confirm the first one, really. And indeed, on Boxing Day 2015, there was a second detection, and they knew then that they were definitely looking at black hole mergers. In 2017, the European gravitational wave detector, which is not far from Pisa in Italy, that detector Virgo joined the network, and this enabled it to observe simultaneously with LIGO, and to enable, as I said, better triangulation on the sky. Then in 2017, there was this humongous event, the famous GW 170817, 2 neutron stars colliding and generating a massive explosion that at its peak was 100 million times brighter than the sun. This was the so-called multi-messenger event because it released gravitational waves first. They arrived first, and then afterwards we detected X-ray, gamma, ultraviolet, and finally, some 11 days after the initial event, radio waves. In April 2019, LIGO and Virgo produced their first catalogue of gravitational wave events, which included at that time 10 binary black hole mergers and 1 neutron star mergers detected between 2015 and 2018. So it showed that the observatories, LIGO and Virgo working together, could produce extremely useful results. In 2019, we had the largest black hole merger ever detected. 2 black holes merged, and the resulting black hole was 85 solar masses. Now, this has raised lots of questions about this class of so-called intermediate mass black holes. Astronomers think there is this class of black holes that are heavier than solar mass black holes, which really go up to about 100 solar masses. And there's a class of heavy black holes between sort of 100 or around about 100 solar masses and up to what we would call a supermassive black hole. So there's a continuum of mass in black holes going right from a few solar masses with the lightest solar mass black holes up to, as we know, the tens of billions of mass, tens of billions of solar masses with the supermassive black holes. I'll just talk about that more a little later on. So in 2020, LIGO had been offline for quite a while to be upgraded to a status called Super LIGO. and the new LIGO was able to detect different events and events further off in the cosmos. And then there was GW 190814. This was the one I was talking about. This was the merger between a black hole and something else, possibly the very heavy neutron star or unusually small black hole. That happened during that period. Then in 2023, KAGRA, the Japanese detector, joined the network. This is actually built underground uniquely to isolate it from terrestrial vibrations, enabling it to do more sensitive observations. In 2023, something else we've talked about before, the discovery of the gravitational wave background using so-called pulsar timing arrays. And there's a video about this on the channel as well, if you want to bone up on that. After 15 years, astronomers in 5 different projects came to the same conclusion that the universe is ringing, if you like, with a constant hum of gravitational waves. And these are thought to originate from the merger of supermassive black holes at the centers of galaxies, although it's worth pointing out that the data fits that scenario almost. There's some little uncertainty about that, and obviously astronomers are on the case to narrow down with further observations exactly what that constant background hum is. What this means, viewers, is that at this very moment your bodies are being stretched and squeezed by gravitational waves, these ripples in space-time. Not very much, obviously. As I said, the waves that we receive up until now, they've been about the 1,000th the width of a proton, so it's nothing you're going to feel. But you and the Earth and everything on it is constantly being squeezed and stretched by this background gravitational wave ringing of space-time, if you like. So that's quite a thought. 2024, astronomers started using gravitational waves as a way of probing the expansion rate of the universe, which is known as the Hubble constant. And that holds great promise for the future, especially as we have what's called the so-called Hubble tension, which is a disagreement between our 2 major methods of measuring the expansion rate of the universe, which still doesn't have a solution. This discrepancy, known as the Hubble tension, does not have a solution at the moment, although there have been some proposals recently as to what could be causing it. However, using gravitational waves, we can actually probe the expansion rate of the universe. So that's a new sub-branch of the new science of gravitational wave astronomy, gravitational wave cosmology. So that's brand new from last year. And towards the future, looking at this, there are plans for a European underground gravitational wave detector called Einstein, the Einstein telescope. We talked about fairly recently the spaceborne, Ian was talking about this, I think last week or the week before, the LISA, the laser-interferometer space antenna, which is sensitive to much lower frequency gravitational waves, such as the merging of supermassive black holes. And that's coming up as well. Oh, sorry, gone the wrong way. Give me 1 second. So I just want to talk a bit about what's going to happen. These plans for LISA and the Einstein telescope. The Einstein telescope is really only in the theoretical stage at the moment. When it gets built, it won't be till at least the mid-2030s. So you've got that to look forward to. But the last 10 years has fundamentally transformed our understanding of the universe. Now, I just want to quickly go over this business of the supermassive black holes. So you've got 2 classes of black holes. They're the so-called stellar mass black holes, which range in mass from about 5 to about 100 solar masses. You've got supermassive black holes, which range from, well, there's no agreed lower limit for the mass of a supermassive black hole, but the most massive yet discovered has 66 billion times the mass of the sun. That's one called TON 618 in a distant quasar. But astronomers have always thought that between the 2, there should be this range of intermediate mass black holes. And one of these detections, as we said, seems to indicate that they do exist. And these intermediate mass black holes can form from 2 solar mass black holes merging. And then that merges with another black hole into a higher mass black hole. That then merges with another black hole into a higher mass black hole, and so on and so forth in a sort of hierarchy, and eventually ends up as a supermassive black hole. Now, there's some question over whether this actually happens, because it will obviously take a long time to get up to the masses of supermassive black holes. Coming up towards the end of this decade, if all goes well, LIGO in India should be finished. Somewhere at the moment, they're saying between 2028 and 2029. That will add yet another gravitational wave detector to the array to enable us to do lots of better science and to more accurately pinpoint where on the sky the event actually came from. So that's what we've got ahead of us in gravitational waves. There's the representation of the Einstein detector being built on the borders between France, the Netherlands, and Germany, where they found an area of soil that doesn't transmit vibrations very well, which is ideal for where you want to build a gravitational wave detector to isolate it from earthly vibrations. LISA, which Ian talked about, due for a 2034 launch into space. As for the future, it promises to unlock secrets of cosmic phenomena such as black holes and neutron stars, which will enable us to understand the life cycle of stars a lot better and fill in some gaps as to what we don't know. And it may be possible in the not too distant future to also detect gravitational waves from the Big Bang itself. If you think about it, these waves are predicted to exist, they should exist, and if they do, they are the only surviving relic of the actual beginning of the universe, because even the cosmic microwave background, the light that was released when the universe had cooled sufficiently to allow light to cross it, even that dates to 380,000 years after the Big Bang. But the gravitational waves may actually originate from a fraction of a second after the Big Bang and are the only surviving relics of that time. So by probing them, we stand to learn amazing things about the origin of the universe. But we have to detect them first. They are such low frequency that it's going to take very, very sophisticated and big technology to detect these things. But theoretically, we should be able to build the technology to detect gravitational waves from the moment of creation with a small c. We may even discover types of objects that we never knew existed. And if you think about it, every technological advance of the telescope has enabled us to discover things we never dreamed existed. That's always been the case. So that should follow that black holes will be the same. Moving on, something completely different. I haven't done a news section this week because it's been a very slow news week. There hasn't been that much in the news. But last week, Europe's Bepi-Colombo probe did its 6th flyby of Mercury before it actually settled into orbit around Mercury. And here are some images released by the European Space Agency and JAXA, because Bepi-Colombo is actually 2 probes in one. When it gets towards its final approach to Mercury before going into orbit, there are 2 probes, a European one and a Japanese one, which will separate and work in tandem to observe Mercury. So this is from the Japanese Space Agency, which is a lovely image of Mercury. We know what Mercury looks like. It's heavily cratered. It's got a really abnormally large iron core, which we still don't know the reason for that. This is what the 2 probes hope to find out. Beautiful image. Another one there looking down on Mercury as it flew by. And another one on the terminator of Mercury. The big crater in the middle, I can't remember the name of it, but the one immediately under that is called Tolkien. So Tolkien is now Lord of the Craters as well as Lord of the Rings. And the one under that, I think, is Prokofiev, after the composer, but a beautiful image of the terminator of Mercury. So there you have it. That's a look at gravitational waves. And I hope you enjoyed that.
Yeah, I mean, these detectors are so, the technology that's gone into them is amazing. I mean, I know when the LIGOs came online, it originally They had to have things like railway timetables because there's a railway line not far away, so they knew if they detected something when a train's going by, that's what it was. But they
Yeah.
could also detect waves crashing on the coasts.
Yes, and in fact, I think I've mentioned this before, that in I think it's the Washington State LIGO, there's a beach 40 miles away, and there's a monitor in the LIGO control room monitoring the waves that it can still be can be detected from 40 miles away.
Yeah.
And of course, the idea behind that is if you know what the signal of the crashing waves look like, and you detect a gravitational wave event, or what you think is a gravitational wave event, you can try subtracting that from the signal to see if the signal disappears. So it's amazing technology, and it's just going to get better and better and better. And
yeah, and because they sort of like happen so quickly, these events,
yes,
the warnings and the detection warnings go out straight away instantly. And then
yes,
the analysis is done afterwards, because the sooner that all the telescopes around the world that are linked to this, the quicker they can zoom around and look where they think the object is. Because in those days, it was, and like I say, in those days, it was only 10 years ago, it was a bit hit and miss because the target area was so big. But with each upgrade, that's become smaller and smaller and
yes,
more pinpointed. And the
yes,
more detectors we get, that'll decrease even more.
yes, absolutely.
Because also, isn't it with the LIGOs, the actual lenses, the reflectors, the mirrors, are held in place by glass threads.
Yes, indeed,
Yeah,
indeed.
that's
They're
right. That
about a
was
millimeter in thickness, and the
yeah,
mirrors. They don't call them mirrors; they call them test masses, but they're mirrors essentially, very sophisticated mirrors, and they are suspended from. What they had to do to fix those threads to the mirrors, they had to develop a technique that had never been done before of welding glass. Now, if you're a welder and you try and weld two pieces of glass together, you know what's going to happen. It's just going to melt. And all of this was done at the University of Glasgow, by the way. It's a Scottish thing. So congratulations to them. The University of Glasgow does a lot of the optics work for LIGO and Virgo, I think, if I remember rightly. They had to come up with all sorts of new techniques to get it to work, and it's the engineering behind all of that is absolutely mind-blowing. Anne's got a question. Just let me put this up on the screen. Anne says, "What's the story about tiny black holes that could even be inside the Earth?" Well, Anne, you're talking about primordial black holes, these absolutely tiny sort of atom-sized black holes that were thought to be born at the beginning of the universe, theoretically. They could be everywhere, and we might not know about them because they are so very, very tiny. But it's all theoretical, and there've been no detection, no observations of it. And the idea of these primordial black holes has been around for a very long time, but no detections. So at the moment, your guess is as good as mine. So there we are. We'll see what the future holds, but they will be difficult to detect. But we haven't seen them yet. Thank you for that. Okay, well, moving on. If you've got any questions about any of that, about gravitational waves and/or black holes, viewers, do put them in the comments. You know, you're welcome at any time to ask us questions. We're more than happy to answer them. So do put any questions or comments in the chat, and we'll do our best.
yeah, because I love the idea that we're constantly being stretched and squeezed and we don't know it.
Yeah, absolutely.
Can I just ask Andy, with this latest thing about the gravitational waves, what do you think would be? I know it's a long shot. And your idea is what the next big thing in astronomy will be? Will it be
what regarding gravitational waves?
Not necessarily gravitational wave.
The next big thing generally.
Yeah.
That
will it be? Pardon?
That's a difficult one.
It is. I mean, I'm thinking along the lines of maybe, planets, extrasolar solar planets, I should say, and possibility of Earth-like discovery of a planet.
Well, you never know, Michael. It may be closer to home than that, because what if either JUICE or Europa Clipper finds strong life at Europa?
Yeah,
there is that.
That could be it, couldn't it?
Yeah, or in Enceladus, for example.
Yes.
But there are no missions planned to Enceladus, but we got 2 missions on the way to Europa, which we strongly suspect of being able to support life. Not that there is life, but being able to, because it has all the ingredients, we think. I wouldn't mind betting that something will be discovered at Europa. I'm not saying it's going to be life, but I think we're going to get a few surprises at Europa, which may overtake what we think we knew. So we'll just have to wait and see. As for anything else, these things come out of the blue sometimes.
Yeah, that's right. And I think exoplanets as well. There's discoveries all the time. But to discover an almost true Earth-like planet out there would be
Earth 2.
Amazing.
Yes, it would be.
Yeah, I think when we get out to these ice planets and that, with the under the ice oceans, even if we don't find life, I think we're going to find some of these very long chain molecules. That will prove that usually the building blocks of life are going to be situated in these oceans, possibly towards the beds of the oceans, like we got the smokers on Earth, where there's a lot of mixing of elements and molecules and everything in these thermal vents. I think it'll be interesting. I think, as Andy said, I think we're going to find something. We're not going to find dinosaurs or anything like that, but or little green men, but you never know, actually. I mean, there could be some sort of
listen, guys, even a living microbe would be a monumental discovery.
I mean, to be quite honest, it wouldn't just be, as you said, monumental, but it's going to change everybody's way of thinking. It's going to be it's going to be one of those things that's going to thump you right between the eyes, and it's going to open us up to new philosophies and everything. So we'd have to completely change our mindset about what's going on. I mean, you're talking about the discoveries. There are so many branches of investigation going on. I mean, look at what James Webb's given us. And that's not looking at what's in the future, that's what's looking at the past. And we've got to completely start rethinking our theories about how this whole thing started, because we're finding major galaxies that are so big and so old when they shouldn't have existed. We've got to completely rethink of how we think this thing goes. So it's not only a case of what's going to be discovered. Have we got to rethink a lot of things that we already think we know? So, I mean, technologists bringing us all this information, and sometimes I seem to think the information we're getting too much data now for us to be able to sit down and think one thing through at a time. Because I mean, you imagine when these big telescopes that are going to come online over the next 10 years are going to give us so much data. We're just not going to be able to cope with it. It's
going to be a fire hose of data.
Oh God,
Which is why, as I think I've said before, artificial intelligence has come along at exactly the right time, because it can do all the donkey work of analyzing this data and even find things that humans might have missed. It's AI is doing amazing things. Before too long, I will be doing a presentation about AI and astronomy here on the channel. It'll either be on here or a video on the channel, so keep your eye on that, because it's an amazing subject, because AI is being used to crunch data to find things that humans have missed or wouldn't stand a chance of spotting in the first place. But this fire hose of data is, we've got the European, before I talk about that, can I just answer David's question? David says Europa Clipper and JUICE. If you ask him what they are, David, then Europa Clipper is NASA's mission to Europa, which is going to go into orbit around it and study it. And JUICE is the European Jupiter Icy Moons orbiter, which is going to do flybys of the Galilean moons with the exception of Io and study them. And both are on their way to the Jupiter system. Europa Clipper arrives in 2031, if I remember rightly, and JUICE arrives about a year earlier in 2030.
That's right. Yeah.
But we'll have these two spacecraft sending back, again, enormous quantities of data about the Galilean moons, particularly Europa, which is our best hope at the moment for finding some sort of life in the solar system, apart from Enceladus. But as I said, there are no missions planned to that where there damn well should be. We need to get to Enceladus.
Yeah,
we really do. So there we are. So I hope that answers.
Derek's asked a question. I've just popped it up.
Oh, is AI better than common sense? Well, AI is not known for its common sense because it doesn't understand the data at all. AI does not understand anything yet. It's going to be soon.
And it has been on the news in the UK today as well.
Oh, really? Oh, well, there you are then.
Yeah, the UK being a provider of AI products, a developer of products using AI, rather than the exporter rather than the importer, according to the Prime Minister, that is.
Yeah. David says yes. Let's go exploring and do the first basic observations. Absolutely. On what's going on around it. Yeah. We do live, David, in at the cusp of a golden age of astronomy. The next decade in astronomy is going to be revolutionary. Now, it's always been said that what we know about the cosmos is doubling every 10 years, but that rate is accelerating. And in the next 10 years, it's going to go off the charts because we've got instruments like the European Extremely Large Telescope in Chile, the biggest telescope ever built by humans, with its 39-meter mirror under the darkest, clearest skies in the world. And that will have a resolution about 15 times the Hubble Space Telescope. So that is going to be quite amazing. We've also got the Square Kilometer Array, the world's biggest radio telescope, 1,000 times more sensitive than any existing radio telescope, split between two sites in South Africa and Australia. That's going to come online towards the end of this decade. What else have we got? In Chile. Sorry, the survey telescope. That's going to come online and again revolutionize our understanding of what's changing out in the cosmos. So, and the American 30-meter telescope, the Magellan telescope, one of which will get built. It looks like the National Science Foundation has been given a choice.
Also, the Roman Space Telescope.
The Roman Space Telescope as well, revolutionary. Was
it the Vera Rubin you were thinking?
Yes, sorry. It's a senior moment, please have some thought for my age. Yes, the Vera Rubin telescope in Chile, which is a survey telescope, which is going to fully photograph the southern hemisphere night sky every 3 months and detect anything that changes. And it's going to do that continuously for 10 years, every night. Because in Chile, I think, the number of clear nights in Chile is a bit like Sparkford, Roger. I think they get about 364 clear nights a year or something like that. That's going to revolutionize our. So that there are lots of new generation instruments that.
I've been to Chile, but it wasn't very clear.
Right. Okay.
It wasn't the accommodations though.
So, this fire hose of data, and getting back to what Derek said, is AI better than common sense? Well, we don't have any choice to use AI with this because it's far too much data. Even if you're a member of the Zooniverse, even if you do citizen science at home at your computer and process data, we haven't got enough citizen scientists to, even remotely tackle that problem. And AI is coming along, as I said, at exactly the right time to enable us to crunch huge amounts of data. And the square kilometer array on its own is going to produce about 5 petabytes of usable data every year. And if you don't know how much 5 petabytes is, that's 5,000 terabytes. And 1 terabyte is 1,000 gigabytes, and so on. It's a massive amount of data, and humans just don't stand a chance of you can put it through computers, but computers, traditional computers, conventional computers, won't be able to spot things that humans would miss. But AI is very promising for spotting things in that data that humans would have missed because of the sheer volume of it, of course. So there we are. So that's what we've got to look forward to, a fantastic decade in astronomy. Stay with us for this decade on Space Oddities, because we'll bring it all to you, every last bit of it. And we're absolutely thrilled to do it. But looking at us, our main worry is if we're going to live that long. So.
No. We'll be AI as well.
Oh, well, I already am. I'm actually somebody's avatar.
Max Headroom.
Yeah, Max Headroom.
Was that the original AI?
Yeah, it was. Okay, well, let's move on. Can I just do a bit of housekeeping? If you would like to support us at Space Oddities, then we'd be very grateful for your money, essentially. You can do it very easily by buying us a coffee by scanning this QR code. Apologies again for the fact that the links to these QR codes are not appearing in the chat, so you can easily click on them instead of scanning the QR code. This is something that I've been working to solve with our streaming provider since September. And even today I was doing tests to try and sort this problem out. So apologies for that. We'll get there. So you can scan that code on the screen with your camera, and that will take you to the Buy Me a Coffee page, our Buy Me a Coffee page, and you can buy some coffee, and anything is gratefully appreciated. And don't forget, we've got the merchandise available at the Space Oddities shop. Too cold for t-shirts, probably. Is it still cold in the UK?
No, underneath your coat.
Yeah, but I mean, is the air temperature cold? This is what I'm trying to get at, guys.
Just a tad.
It's actually going to get warmer tomorrow.
Is it?
Yeah.
Yeah. Well, we had a warning for low temperatures last night. It went down to -4 last night. So, and we got the same warning for tonight. So I'm going to wrap up warm in bed.
Have you got that temperature scale in Spain, Andy?
Sorry?
Have you got the minus temperature scale in Spain?
Well, yeah. I mean, don't forget, we're not far from the Pyrenees.
Oh, okay.
And the cold air from the Pyrenees at night comes down over the plains and really cools everything down. So it gets to -4. So, it is known. I mean, we don't have snow here very much. I think the last snow we had was about 8 years ago. So, we don't get snow. But when we do, it tends to be a lot.
Yeah.
And we had the famous snows of 2010 when we were snowed in with no electricity for the best part of a week. That was fun. Lots of people in our village didn't even have any water because there was no electricity to run the pumps. We, luckily enough, did have water because we're slightly outside and on a different system. But it was terrible. It was just an awful week. A lot of fun though, but not what you want really. Okay, yeah. Let's just remove this QR code. And there we are. So let's move on now. Now, Daz, you're going to talk to us about the Parker Solar Probe, I believe.
Yeah, I sure will. Roger, have you finished with your presentation? Roger? Anyway, wait a second.
Okay.
That's the wrong one. Just remove that. Right, okay then. Can you see that?
Yep.
Right, let me just go to PowerPoint. Right, as we all know, regular viewers of our show, since November, we've had very little data coming from the sun. Or saying that's not actually strictly true. There was an incident at Caltech University, and that's where all the data from the Solar Dynamic Observatory comes in, and it's stored in computers and data banks. There was a leak of cooling fluid. It flooded the room, and so we basically not didn't lose the data. In fact, I'm actually showing you the wrong thing at the moment. But what happened is the data comes into the Caltech, it's analysed, it's sorted, and then it's sent out to all the places it needs to go. And unfortunately, lots of the apps that space weather predictors and everyone or people interested, um, they didn't basically they couldn't get hold of the data that they required. So we've been unable to actually bring you a decent. Sorry, I'm on the wrong. This is my bad. I will be with you in a minute.
Okay. Yes, it was a failure in a cooling system, wasn't it, Daz? That leaked.
Yeah.
And, took everything offline.
That's the one I want. Yeah, that's it. Yeah, so it all went offline, so we were unable to get the data we need to produce any sort of like worthwhile space predictions and things like that. And if you remember, and also last week, it's back online now. Some of the data, but of course they've got to now load all the data that they stored in New Mexico into the system, get it analyzed, and start sending it back out. So it's probably going to be at least probably another few weeks, if not months, to get all the data up and running. So basically, what I want to talk to you about now, anyway, because I went off on that spiel because I was showing you the wrong. That's for a bit later on. Right, what I was going to talk to you about. This was going to be one of my presentations for what was the best of 2024. And of course, for me, it had to be the Parker Solar Probe. As we know, it was launched in when was it launched? They started to look at it in 2017. I think it was launched in 2018. So, but the actual probe is named after Eugene Newman Parker. He was an American astrophysicist, and he developed the theory of the supersonic solar wind that affects Earth. We've heard us talk about it before. It also carries the CMEs and the radiation from the big expulsions of data from matter from the sun, which travel to Earth, and then they have an effect on us. Now, this is the first probe or satellite that's ever actually was named after a living scientist. And so he was. It was named in 2017, but unfortunately, Parker he died on March the 15th in 2022. So he didn't unfortunately see the best part that was to come from the Parker Solar Probe, which is basically designed to fly as close as it can to the sun. So, right. So what the Parker Solar Probe is, it's designed to actually look at the corona. It's actually designed to fly through the corona and basically give as much information as we can about the solar wind, the actual activity that's happening on the sun's surface. And as you can see here, this is a CME that was from 2024 on the 15th of December. And as you can see, it's a massive expulsion of material. Luckily, this one is heading west, so it was going to miss us, but there was a good chance that we were going to get the side of it. So we need to know what is coming our way. And the only way we're going to find that out is to find out how the sun works and what we are looking at. So this is a CME in two different wavelengths. And as you can see, You can see the bulge on the right-hand side, on the orange side. You can see all the matter being pushed away. But when you look at it in a magnetic form, you can see more of the actual formation of this CME as it is. And the red line is actually showing you the boundary of where this actually thing. And we look at these, but we also, when we look at coronagraphs, we look at them in 2 or 3 different sizes and scales so that we can estimate the speed at what these things are trying. And again, this is what Parker Solar Probe was on about. So as I said, you get an expulsion from the sun, which is on the left-hand side. We've got the solar wind blowing constantly towards us. You get an expulsion of matter that will travel towards us, and it will then affect our magnetosphere, which is our protection from all the sun radiation from the sun. So what we need to know is what's happening at the sun end of this. We've got a good idea of what's happening at our end, but we need more information about what's going on this side. And as you can actually see on the sun itself, if you look at the edge of it, you can actually see they put it that's actually vibrating, because that's what the sun does. So, of course, not only does it predict us, help us predict what radiation storms we're going to hit by, but it also means we can predict beautiful images, beautiful events like this, which are aurora. Now, what's happened here is the energy, the extra energy from the sun has come across the interplanetary plane to us. It's hit the Earth, and what happens is if everything's all lined up, if everything's correct, the radiation from the solar energetic particles will come back, and it will actually, they will be funneled down in through the north and the south magnetic poles. And as it comes down through, it'll excite the atoms, different atoms in the actual air, in our atmosphere, and this will excite it, and it actually glows, and you end up with this beautiful aurora. And as you can notice, we're looking at here at the Pleiades. You can see the Pleiades just left of center there. But the different colors usually give us an indication of how strong this is. And also, the stronger it is, the lower it will push down in latitude from north and south. So it comes from the south and the north, and it rolls down towards the equator. The closer to the equator it can be seen, the stronger the actual magnetic disturbance is in our atmosphere. So this is what we're looking at. We need to know these things, because not only does it give us beautiful things like this, but it can actually have devastating effects if we're not ready for it. It can affect satellites in near-Earth orbit. It can affect ground-based systems like electrical power stations, because we can all remember the Carrington event, which is sort of like the benchmark of all solar storms, when the telegraphy was Morse code was being used a lot, and it was just coming into its power, and the operators were getting minor electric shocks, and because they used ticker tape as well, there were some fires caused by it, and that was by currents being induced in the lines that were strewn all across the country. And they were able to disconnect it because it was all run on batteries. They were able to disconnect it and still run the telegraph as without the power connected. So that's what we're looking at. So we need to know this sort of thing. So ever since we started to send things into space, heliophysicists, people who predict storms, space weather, and things like that, have always wanted a probe that will fly as close to the sun as possible and look into the coronosphere, where all this, most of this is happening, and see exactly what's going on. So they decided to build this probe, which they, as I said, they called the Parker Solar Probe, and to protect it, because it's going to go very, very close to the sun, they built a massive heat shield, and you can see it on top of the probe here. It's the big black sort of like slab that's on the top. It was 11.43 centimeters thick, and it was formed from reinforced carbon composite material, which was able to withstand temperatures up to 1,377 degrees centigrade, which is 2,500 degrees Fahrenheit. It also had reflective coatings put on it, ceramic paints, and things like that. This had to be specially designed, and in it, so the actual probe could do its job. There is actually holes cut into the shield, which open up and allow cameras to operate and instruments to take their readings and things like that. But as you can see, the whole of the probe is tucked behind that heat shield. So when it's going past, that heat shield must be directed at the sun to protect everything in the back. And it does run on solar panels, and even the solar panels have to be folded back down as it goes past the sun. And there is also a water cooling system on there. So just to help it out with, and I think that is actually to help dissipate the heat in the instruments on the actual spacecraft itself while it's doing its flyby. So here are the instruments on there. You got, if you go online, you can read what all these instruments do. They're measuring solar wind electrons, protons, and alpha particles. ISIS is energetic particles, fields, antennas, electric and magnetic fields. You've got wide field visible light imagers, and everything like this. And this is all tucked, and it sits behind this big thermal protection system as it flies by. Now, the reason it was launched on 2018, August the 12th, using a Delta Heavy rocket. And once it was in space and it was released, to be able to, of course, as you know, with the laws of gravity and things in orbit, if you're close to an object, a big object, to stop being pulled into the object, you have to travel very fast. And to achieve this, the Parker Solar Probe had to do several flybys of Venus. So it would go round the sun, come back out to Venus, and it was slowly using gravitational assist, or sort of like a catapult using the gravity. It will get faster and faster, which means it could get closer and closer to the sun. And also it'll adjust the angle so it will, as I said, get close to the sun. It did earlier last year. It did do a record-breaking. As you can see here, here's the orbit, using the gravitational assist of Venus to get closer and closer to the sun on each flyby. So last year it did do a flyby Venus, and then it did a flyby of the sun, breaking the record. But the actual eventual record was broken on the 24th of December, 2024. So on Christmas Eve, just gone, the Parker Solar Probe, while we were preparing our turkeys and everything, the Parker Solar Probe was actually whizzing past the sun at a tremendous speed. Like I said, it's done several flybys already, and it's found some really big, as well as discoveries. It's also being used to confirm or deny the way we already think things are actually going. Even during its initial orbits, Parker Solar provided unprecedented measurements of the solar wind, revealing new details about its behavior. The craft detected switchbacks. Now, these, if you might have seen some images taken by the Parker Solar Probe of if it sat in the solar wind, and then if you look at the particles streaming by, they actually switch back. They turn back on themselves and then come back. And these zigzags could be related to solar wind as it accelerated and heated, but also these originated actually on the surface of the sun when events actually happen. So they've been able to confirm these things. And these are sort of like will be part of these storms that hit us. These findings challenged prior models and demonstrated the dynamic and complex nature of the sun's environment. Detailed investigation of corona structures. That was it's sort of like Parker data has revealed detailed images of data of coronal loops and plumes, helping scientists visualize the structures of the sun's corona. It discovered that the corona is much more dynamic and turbulent than previously thought, constantly changing in its structure. These, and of course, these observations are crucial to know how they're generated and how it affects our space environment. So, like I said, you can read these. You go back and stop these and have a look at these. It's discovered rogue waves, detected small-scale solar bursts and events, and provided insights how plasma is heated and accelerated in the corona. Refined understanding of the solar wind, measuring plasma and magnetic fields near the sun. It's been doing all of this, and this is the sort of image you can see. Now, this is a spiral formation actually photographed or was able to image actually in the solar wind. All these streaks are energetic particles, radiation particles zooming by out into the interplanetary space, and then you've got this spiral circle. Now, my theory is, and I'm just sort of guessing here, that this is a CME that's just been ejected, because if you look at it, it reminds me of these solar slinky that I've told you about, which is the form that is taken by a CME, and it looks as though we're looking down one end of it. So possibly, I don't know. I don't know enough, but that's what it reminds me of. So the Parker Solar Probe, this is sort of like just a timeline. It's about the discovery of the switchback down in the bottom right hand, the switchbacks. And as I said, they've since in the further passes have linked these two events that are happening on the actual sun's surface. And the final closest approach, as I said, if you look on the right hand side where the sun is, the closest approach, which is 3.83 million miles. And that was on December the 24th. So that was Christmas Eve. So there we go. So it went past it, like I said, expected to be during the flyby, spacecraft will reach one of its closest approach to the sun, expected to be around 6.9 million kilometers or 4.3 million miles from the solar surface. This is closer than any other spacecraft has ever been to the sun. So this is the closest thing a man-made object has actually been. At this distance, will be subject to intense solar radiation, extreme heat that would challenge its heat shield. So, of course, as with anything, when you do these sort of things, you don't know whether they're going to work. I mean, when this thing flew into the corona on its closest path, then we didn't know what was going to happen, because, of course, you lose touch with it. It's the same as a capsule coming through the atmosphere, returning to Earth. You lose radio contact. So scientific goals of during the flyby, again, processing the processes that create solar wind, how energy is transferred and stuff like this, CMEs and all that. So if you want to go back, have a look at this, you can get an idea of what it was actually doing. The solar magnetic field mapping, again, it was mapping the corona's magnetic fields, which of course are always changing. We know even on the surface of the sun that the actual it's changing every time, every minute, and it's during these magnetic fields, when they get complicated, that's when we get these eruptions that we need to be looking out for. So there we go. So what did it survive? That's what the question we got to ask, and of course the answer was yes. It was a success.
Yes.
A beacon tone received in the Mission Operations Center at St. John Hopkins Applied Physics Laboratory in Laurel, Maryland, late on the evening of Thursday of December the 26th, confirmed the spacecraft had made it through the encounter safely. So that was the indication that the thing had survived. Everybody was amazed that it did, because of, I said this is all new technology. With the thermal protection system, the shield hold up, and of course it did. So yes, we got through, and I do know also that since that, we've had further communication. Again, I think that was on the 31st of December into the 1st of December, where it's basically been starting to send some of the data back, checking all its systems out and things like that. So very soon we will be receiving all the data it's collected, and then everybody can start analyzing it and hopefully find out a bit more of just how the sun works. So the future for the Parker Solar Probe. So, excuse me. So the 24th was the closest flyby. There are another 2 more flybys planned for the sun, but these will be at the same distance. It's not going to go any closer. They think they've pushed their luck far enough. And the 2 flybys will be on March the 22nd and June the 19th. So, and they, as I said, same distance and the same speed. Because this actually broke the record for the fastest man-made object.
I think I remember reading, Daz, that at the speed that it was flying across the sun, it could go between the east and the west codes of the United States in 30 seconds.
Yeah, it was a humongous speed. I thought I had it written on here, but obviously I've missed it somewhere.
It was 430,000 miles per hour.
Excellent. Yeah. Imagine what it'd be like if you took the handbrake off. But yeah, it's absolutely fantastic. Yeah. So in conclusion, the Parker Solar Probe is an extraordinary scientific undertaking that is transforming our understanding of the sun and its influence on not just our planet, but the solar system. December the 24th, 2024 flyby was just one of many close encounters that will yield unprecedented data, leading to further breakthroughs and advancements in the years to come. This bold mission is not only a testament to human ingenuity, but also a shadow into the fundamental processes that drive our star. So I just thought I'd like to put out there, that's what was one of my highlights of 2024. As I said, we're getting the data now. I know we're in 2025, but I still think that 2024 for solar observation, this was the biggest achievement possible. So I do believe
if I remember rightly, Daz, NASA have said they plan to release the results of the flyby on January the 30th, if I remember rightly. So
okay.
Right,
Right, here we go. Let me just get rid of that for you.
Thank you. Okay. So I think we will start wrapping things up now. Just a reminder, we've all got an early start tomorrow morning again, where we're going to bring you at 6 a.m. British time the launch of the Blue Ghost lander to Mars, and a Japanese lander as well. Let's not forget that one. If you would like to know more about the Blue Ghost mission, well, we've created a video that will tell you all about it. And if you go to our channel, you will see this, which is the video in question, and that will tell you all you want to know about the Blue Ghost mission, which is actually really exciting because, as I said earlier, it's the start of a year of quite intense lunar exploration with all sorts of missions bound for the moon this year in an effort to know more about it and to test technology for perhaps, hopefully, humans having a permanent presence on the moon one day. So in the not too distant future, we hope. So there we are. Okay, we hope you
to do a quick sun report. What I can do.
Oh, have you got a quick sun report?
Yeah, just a quick one. That's
Okay,
what I
cool.
started playing for you earlier. It was the wrong thing. So let me just share this. Can you see that?
Yes, we can see that. Hang on 1 second.
Yeah.
I need to try it. There we are. Oh, it's gone again. Okay.
It's gone.
Yeah, you try again.
Let me just come back. Alt tab. Let's have a look. Here we go. There he is there. So let me just put him back up again.
There we are.
Okay.
That's it.
Right,
Yeah.
let me just go to... Right. Okay, then let me start this again. This is what I started earlier. As I said, we have got some the SDO back up and working, so I'm able to bring you some videos now. I would just see if I can start this one again for you. So this is a week. It's not a full week actually, because the data that they've uploaded isn't taking us back a whole week. But again, here we are. Here's our lovely sun that we've been missing. This is the sun I saw in Lanzarote. I wish. But yeah, it was absolutely gorgeous. You can see there's a lot of filament action going on. Before I went to Lanzarote, I was talking to Andy, and I said I had a feeling the sun was going to do something over the Christmas period. And it did to a certain degree, but things didn't line up, so we didn't get any aurora. But then it started to really pick up, and then on January the 1st, we had some lovely auroras which were captured in the UK. So now the reason I've put this up, and it's at such a small scale, is that's just coming in is Comet Atlas that Roger was mentioning earlier. So again, it's a lovely, beautiful comet that's actually flying closest to its sun, and we can actually see it here. You can see the tail in lovely detail here. And here's the latest image that I got earlier. So it's virtually traveled all the way across. Give it another day and it'll probably have disappeared completely. But I just thought you'd like to see that. That's something that's been going on. So I'll move on. Now, this is the reason, but also what we've had a lot of in the last week or so is coronal holes, and they have been massive. This doesn't cover all of them. This is only covering, I think, from the 8th. But you can see this black thing in the middle, that is your coronal hole. And I'll put to the left a scale so you can see how big these things are. And as it comes towards the center, you'll see what's coming from the west is getting darker and darker. Now, remember, this is the origin of a lot of the enhanced solar wind that comes towards us. It's not a hole in the sun. It's just that this is taken at 211 angstroms, the wavelength, and this is showing us all this pink stuff, all the magnetic structures that are on the surface of the sun. But where there is very little magnetic action going on, the actual surface of the sun is cooler, and that's what we're seeing. It's not trapping the magnetic fields are spreading out into the corona, and they're trapping all the heat and the radiation next to the sun's surface, and that's why we're seeing what's all this that's in the pink. And again, of course, the light areas are the more intense, and the darker areas are the less. So what it is there's a gap between these active regions, which is cooler, and this is what the dark region is. If you can see my cursor, which I can't, here he is, just in here. It actually comes around through here, but because our perspective, we don't remember this is a sphere. It's not a flat plate. So as it goes round, then our perception of it changes, and the hole still carries on round here. So there is the Earth size that gives you a rough idea of how big it is. So what's happening is the heat and radiation of the particles can actually escape out into the coronosphere and then travel out on into the interplanetary space, which then comes our way or in whichever direction it is. The next one will give you more of an idea of the size of it. Hope you can see that the scale of the Earth to this big black hole that's virtually sat in the center now. And of course, this will blow stronger winds towards us. And of course, this can actually give us auroras in its own right. But if one of these, if say this area here has a CME go off or some sort of filament lift off, it will be caught in this wind. All the material that is thrown off will be caught in this wind and pushed towards us faster, and it will give it more oomph. So so that's what it is. So I just thought you'd like to see the size of this thing. Absolutely amazing. This is the synoptic map for this week. Remember, this shows us everything that's been recorded on the sun today. They draw this twice a day. Of course, you can see your neutral boundaries between negative and positive areas on the sun because it's all mixed. You've got your active regions, which are numbered, but you'll see on here we've only got about I've got 1, 2, 3, 4, 5, 6, 7. We got 7 marked on here. Now, over the last week, we've had up to 13 active regions, and I'll show you a picture of this. As you can see, here's that big coronal hole, and that's the bit that I was on about, which, although it didn't look like a hole, it was there because we're looking at it a different perspective. And it's a negative. So that will, and the positive and negative fields in these actual regions, there is an effect that the solstices, that if it's positive, it has more of an effect. If it's negative, it has a reverse effect, sort of thing, depending upon what solstice we're closest to. But you can see there's some all this red, pink stuff. That's the activity that's going on. You got your regions with their predictions of C flares, M flares, and X flares. But there's not really that much going on. They're saying there's a 10% chance of an X flare from these here, and that seems to be they're hedging their bets on 3959. So we'll move on. So these are the active regions we've just been looking at. As you can see, they're pretty simple. They're alpha or beta, but we do have a beta gamma with 3947, and that this last week has given us some amazing action, but most of it away from us, unfortunately, before it faded. So this was about a week ago. This is the third. And as I said, 3947 was just coming onto the eastern region here. Now, as this traveled a path, before it even got to about this region, it gave us some really impressive X-class flares. Again, look at the size of the coronal holes. It's these things here with the hashtags inwards. And here, they're really big. They are really large. But here, I think we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 numbered, 12, sorry, 12 numbered active regions on here. And of course, this is where we're going to get our sunspots from. But it was this one here that gave us a load of action last week. And in fact, on the 3rd, obviously, because this was done 4 o'clock in the morning, within a few hours, this started producing X flares. So this is what we had before Christmas. From Christmas to New Year. As I said, on the 1st of January, we had some really lovely auroras. And you can see it here. We reached over between G3 and G4 storm ratings, and that's what gave us these lovely auroras. So on the New Year's Day. So again, and then since then, this is since there, you can see it's been quite active. Again, most of this is from 3947 coming down, but you can see over the last week, we've even reached a storm G2 there on the 4th of January. But from what it was before, let me just pop back. As you can see, leading up to a New Year, there was virtually hardly anything. We're bouncing along the bottom. But since then, things have been a little bit active. So yeah, things are moving on quite nicely. I didn't want that. Yeah. Now, as I said, on the 3rd, and a little bit later from when that image was taken, 3947, it actually gave us just over 24 hours 4 X-class flares. So these are images of 3 of the flares. I was unable to find an image of the 4th one. But as you can see, there was a 1.21, there was a 1.1, and then there was a 1.8. And I think the one that's missing, it was an X2. I think it was 2.4 flare. But as you can see, because of its position, most of that was away from us. And we only caught sort of like a bit of a tail end of it, which is why we've been getting that bouncing along, quite rugged plots on the on here. So it's thanks to 3947 that's virtually given us most of this, but now it's fading. So there we go. Now we were talking about Andy and ourselves were talking yesterday on our live stream about the solar storms this time, and I was remarking about Bartel's music sheets, and this is what they are. You can see the link at the top there. All you have to put in is basically Bartel's music diagrams, and then what you're looking for is this KPGFZ. And once you see that, just click on it and you can come onto these. This is from September last year up to basically yesterday. And you can see what you've got here is each one of these lines is you've got your days here. Now, this is the date. This at the top is the days in the rotation. It takes 27 days for the sun to rotate. So this will give you whereabouts in regards to the rotation that each day was. So if you want to know the date of the actual events, you have to look along the bottom of the lines. Now these are all KP readings. Each line is between each line is 3 hours. So you'll get 6 of these. No, not 6. Maths is gone. So between each of these is 3 hours, and this will tell you how high the KP index actually reached. Now, so the KP indexes can reach quite high, but it doesn't mean you're going to have a storm with them. Once they start doing get high, if there's a storm behind them, that's what these solid lines are. So this is so we had some storms here, and this is probably about a G3 G2 2-3, and then of course you got the bigger ones here, which give us, as Roger was saying, his background is from this event, which was an aurora event that we actually saw. And then if we come all the way down to January to December and the 1st, it looks like it's given us the finger. That was the event that gave us the aurora on New Year's Day. But you can actually, if you come on here, you can actually, it's interactive. You can actually go back to about the 1930s and you can see every day from there all the way up to today. And you can see when we get big clumps of storms. And you'll be surprised at how many storms you've actually lived through, but you've probably never noticed. Yeah, we were talking about it, and somebody asked about the Bartel's music sheets, and this is what it is. This is what it looks like. It looks like a musical score. So I thought I'd put that up so that people can see. But yeah, what you're looking at is events here. So yes, we have. It's only been since last March that we've had some events. Some of them gave us aurora, some of them didn't, because remember, you've got to remember everything's got to line up, all the ducks. So I'll leave it there anyway, and then if you've got any questions, let us know and we can talk about them whenever you're ready. So okay then. So
thank you, Daz. If you could just remove that.
Yeah, just doing it now. Here we go.
Thank you very much. Well, but that's it from us for this evening, viewers. We hope you enjoyed our ramblings this evening. We will be up early, as I said, tomorrow morning for the Blue Mission, Blue Ghost. I'll get it right in a minute. The Blue Ghost mission, early morning for us, and we will be live at 5:45 tomorrow morning here on Space Oddities. So we hope you can join us. Then, of course, tomorrow night we've got the Starship Flight Test 7 going on, launching allegedly at 10 p.m. UK time. And then Thursday morning, really early again, at the same time, 5:45 will be live for the second attempt to launch Blue Origin's New Glenn rocket. So we hope you can join us for those events. Full details on the channel, full details on our website, and that's it. And it's hard work this week, but we're enjoying it, I think, aren't we, guys, so far?
Yeah. Yeah, but by the end of the week we'll be zombies. I'd just like to say hi to Ian. He's just come back in from his
Hi, Ian.
Astronomical Society. Hope you had a good night. And he's only just come in, and he says he's a little bit frayed around the edges by the sounds of it.
No change there.
Bless him. He's ready for his cocoa.
Yeah.
Ready for his
Yes.
All right then. So we will bid you good evening. Thank you so much for being here. We do appreciate your company, and we'll be back. Apart from all the live events this week, we'll be back for another tour of the universe, bringing you everything about the cosmos. Same time next week. So do join us. Do keep your eye on the channel. We've actually got a couple of new videos up on the channel that you might like to look at. We do our best to bring you the universe. If it's happening in space, it's happening on Space Oddities. That's what we always say. So from all of us at Space Oddities, thanks for watching, and we will see you very soon. Take care of yourselves. Be good.
Hi, everyone. Happy New Year again.
Each other all